I'd like to thank everyone for showing up today for our Chemical Toxicants in Water, a GeoHealth perspective in the context of climate change. This has been a workshop and webinar in the works for about a year and a half. So I'm very glad everyone can make it. And I thank all of our speakers for being willing to participate. I'd like to introduce myself. My name's Kathy Proper. I'm a professor of biological sciences and an affiliate with the Southwest Health Equity Research Collaborative and the Center for Health Equity Research at Northern Arizona University. I'd also like to introduce my collaborators on this project, Dr. Alan Kolak from the University of Idaho, the Water Resources Research Institute, Jesse Bell from the University of Nebraska, the Dougherty Water for Food Institute, and Shannon Bartelt Hunt, also from the University of Nebraska, and the Dougherty Water for Food Institute. I've been doing research on chemicals in water and how they affect vertebrates for over 20 years now as models for the impacts of these chemicals on human health. I'd just like to start by riffing really off of the rhyme of the ancient mariner, with water, water everywhere, and all the boards did shrink. Water, water everywhere, nor any drop to drink. And this is really a metaphor for the issue of water pollution in the context of climate change. The mariner was first stuck in a cold southern sea, and later in a very hot and dead sea filled with noxious things. He ended up there because he shot the albatross, which was protecting the health of the entire crew. Really, we are the mariner. His protector was an albatross, our water, and his shame was really the death of the albatross. So how do we save our own albatross? We're just now beginning to recognize the intersection between really this chemical tidal wave we're facing and the issue of climate change and that intersection. And our plenary speaker, Gabe Filippelli, will speak to this intersection between chemical pollution and its impact on human health. These two papers, one is just out, Chemical Pollution, a Growing Peril and the Potential Catastrophic Risk to Humanity. It has just been published online. And Dr. Filippelli's paper, Addressing Pollution-Related Global Environmental Health Burdens, is an important read to understand really the depth of this problem. Indigenous people everywhere say that water is life. We know water drives and supports every single function, from molecules to ecosystems. And we know that there's a pollution effect on climate change. We certainly know that molecules like methane and CO2 impact climate change. Here we're experiencing severe drought conditions where I'm sitting right now. In fact, I woke up to forest fire smoke in the bedroom this morning. Flooding, though, is also a huge problem. Now, what is really, though, the intersection between drought and the chemicals we find in water, and then how those chemicals can then feed back into the water that comes out of issues associated with climate change, such as flooding? And there's really limited research on this intersection. So I want to talk about what the format of our 3 days is to really get at this issue. And I encourage you to please go for our agenda to this website. It's also in the chat box. The way the format will work is each day will start at 9, and then at 9:10, the speakers will each have 30 minutes to present their talks. From 10:40 to 10:45, we give everybody a quick break, and then we'd like to ask you to return into breakout rooms, and we'll assign you randomly into breakout rooms with each speaker and one of the organizers. And please be ready to do a quick written introduction of yourself in the chat box. And if you're comfortable, you can leave your video on for the discussion. But if not, feel free to either just unmute and shout out any thoughts or questions or throw them into the chat. If you're comfortable to leave your video on, that's great, but you don't have to. The questions we'd like you to think about are, what did you derive as the biggest problems needing to be addressed from the speaker's talks each day? And then within the realms of scientific research, education, and policy, Is there a way to define focus tools moving forward? We'd like to reconvene as a large group between 11:15 and 11:45, and the moderators and speakers will summarize their group's discussion. And from 11:45 to noon, we can have a big group discussion on what are the big questions. I'd like to give a special thanks, excuse me, to the Arizona Biomedical Research Commission and the Arizona Department of Health Services, and especially Doctors Julie Baldwin and Robert Trotter, who are the PIs on the grant supporting this program. I'd also like to thank the Center for Health Equity Research at NAU for really helping host this webinar, and the Idaho Water Resources Research Institute and the University of Idaho, as well as the Dougherty Water for Food Institute, excuse me, and our co-organizers, Alan Kolak, Shannon Bartelt-Hunt, Jesse Bell, and of course our plenary speaker, Gabe Filippelli. I'd also like to give a special thanks to all of our speakers over the next 3 days. They'll be introduced each morning. Special thanks to our support team at CHER, Amy Gillette, Marcel Coder, Lisa Dom, and Erin Gencarelli. The albatross is really a symbol of our need to address the water issues that are coming down the pike. So I'd like to end by coming back to the metaphor of the rhyme of the ancient mariner and the albatross as a symbol of protection. Once the mariner shot the albatross, disaster struck the ship, and the albatross was hung around his neck by the other crew members as a symbol of his shame. Water really is our albatross. Climate change and pollution are now among humanity's shames. For the mariner, prayer released the albatross, but we're going to need more than that. The mariners, to free the albatross, we're going to need to both increase communication about the current risks facing the world with water crises. And as scientists with expertise, we need to be creative in the research we use to address these problems. We offer you all the opportunity each day to stay in the breakout rooms and help us work towards the next steps and hopefully shake that albatross from around our necks. With that, I'd like to introduce our speakers for today. We have Gabe Filippelli, the Chancellor's Professor of Earth Sciences and the Executive Director of the Indiana University Environmental Resilience Institute. He is also the Editor-in-Chief of the journal GeoHealth. Mary Ward, Senior Investigator and Occupational and Environmental Epidemiology Branch in the Division of Cancer Epidemiology and Genetics at the National Cancer Institute, and Avner Vengosh, Duke University Distinguished Professor of Environmental Quality at the Nicholas School of the Environment. I thank all of you for being willing to support this webinar, and I look forward to the outcomes. Thank you. Dr. Filippelli, I'm going to pass the screen on to you.
Well, thank you so much, Catherine, and I hope everyone's hearing me loud and clear. It's a real thrill to be part of this really innovative format that has been developed for the next 3 days. I'm going to do the normal awkward shifting to the share screen, so bear with me. Never figured out a way to do this seamlessly while stuttering through this, but nevertheless, here we go. So GeoHealth is, as I'll be introducing through this brief presentation, is a relatively new term, but the actual concept has been around for quite a while. And there is no more important time to be engaged in a conversation like that than now. We have seen this play out in terms of the intersections between the environment and humans in a vicious way with the current pandemic, as well as in the host of natural disasters, many of which are not actually natural at all. They're caused by human-caused climate change, and it's coming to roost, actually. It used to be climate change was a theoretical threat multiplier is considered of natural resources and human sustainability. but in fact, we're seeing it in the here and now. And that's why I was thrilled to see the topic on water and drinking water and climate change, because just like last century was a century of oil, this century is the century of water. And I would argue that next century is a century of phosphorus, but that's a conversation probably for another day. But water is going to be central, and water sustainability and quality are going to be central to a lot of how countries are resilient or not to climate change. And so I would like to take this opportunity over the next several minutes to introduce the concept of geohealth, what exactly I mean by it, and what we as a community might come to think about it by the end of these 3 days, because it might be different coming in than it will be by Wednesday. And frame a couple examples of what I call really calls to action by our community. And one of them will revolve around our need to embed community, meaning not the scientific community, but the actual communities that are impacted by climate change, by water resource issues, by chemicals and toxicants. Engage with them in this dialogue of maintaining resilience to climate change. But also, I'd like to add in a special call for equity, considering equity in many things that we do. And finally, we clearly need a better way to train the next generation and to support them once they're trained via funding. So I'll be stepping through a number of those calls to action. But first, let's start off with just the general concept of why is it important that we have geohealth? Why is it important that we understand the intersection between environment and the human health? Well, it's pretty straightforward, right? We're always told that our health and well-being is a mixture, a combination of the environment and our genes, right? And they come together in some proportion. It's not a fixed proportion, but in some proportion to lead toward our own health and our own longevity and our progress through life, whether it's a disease progress or a progress of wellness. If you think of this in another context, though, I kind of consider it this way, because it's, I think, easiest to think of the actual vast separation there is between the fields of earth and environmental sciences on the one side and human health sciences on the other side. I just came off of listening to my niece, who's a pediatric fellow in Seattle Children's Hospital, getting praised as she's finishing up her fellowship and launching into a pediatrician by all of these doctors who look at pulmonary health from one very particular perspective, right? And yet, on the other side, environmental scientists are trained to understand quite a bit about how geological materials or human-produced materials might impact pulmonary health. But rarely do those two things come in close proximity to each other. Or in other words, rarely does an earth scientist inform a pulmonologist about practice, nor the other way around. And this is seen by how messy some diseases are. One classic case is mesothelioma, where for quite a long time, and this follows with silicosis as well, there was a real head scratching of these lung diseases. What is causing these lung diseases? We clearly know they're occupational, most of them, but it was initially, we cast a broad brush on asbestos, as if asbestos was some uniform mineralogical material, right? And the earth scientists on this webinar know that that's exactly not the case, right? Asbestiform minerals come in a range of chemistries, a range of potential reactivities, right? And most particularly a range in needle shape, right? Shape of the actual minerals themselves, which ended up to be the critical component to inform our understanding of how some kinds of asbestiform minerals do cause significant pulmonary disease, whereas others are completely benign. But we painted asbestos with a broad brush and gotten rid of it everywhere. And that's one example of this disconnect between what we know from in this case, I used a pulmonary example on purpose, a pulmonary outcome and an environmental driver, right? In this case, there's almost no genes in between the two, right? Exposure to needle-like speciform minerals is likely over the long term cause you mesothelioma. Right? Similarly, the chasm can be great between them. And I'll give one example that's more appropriate to this particular workshop: lead poisoning, right? The tragic case of the Flint water crisis was one that was actually quite predictable. And I'll go through that in a little bit more detail in a couple more slides. But this is a case where it's not like the earth scientists and the water scientists, water engineers had predicted that there'd be a huge uptick in lead poisoning in Flint, Michigan. And so then they worked with the health authorities to figure that out and see if they could find if their prediction is true. In fact, of course, we know it was an unplanned experiment. And the only reason why environmental scientists were brought into the equation was because a pediatrician in particular was noticing a significant uptick in lead poisoning among patients, pediatric patients. After pretty long declines, right? Decades or two of decline, and all of a sudden you get this big uptick. Well, it took about 18 months for that information, that lead poisoning information, to really cause positive changes in what we understand as the root cause of that lead poisoning, which is, of course, a change in water sources, which means a change in water chemistry. And those 18 months, it's not a trivial point of statistics, 18 months. That's 18 months of lead poisoned children, 18 months of lead loading for children, and they'll never get those 18 months back again, right? And most of you know that lead poisoning is permanent. And we're seeing now those infants who are poisoned in this one interval, right, now are coming into elementary schools in Flint, Michigan, needing significant educational services because of those impacts. Not only that, but Flint itself its task base has decayed. So here's an example where you have a poisoning event where the victims are barely even getting recompense for the damage done to them. And this, again, is a characteristic of this vast separation between the health sciences and the environmental sciences. And you'll see a little bit later on what I mean by the call to actions. Of course, we need to figure out a better way to bring those two spheres closer together. One of the constructs that we've been using, of course, to consider the holistic, the sort of One Health approach, if you want to use another term for it, is GeoHealth, right? Is to understand and acknowledge this continuum. And embedded in that continuum, that GeoHealth middle, is a whole, I usually consider them as a whole set of layers, right? There are the layers that some of us as scientists and practitioners are very good at understanding. For example, the bottom layer, contaminant source. Let's say you have a zinc contamination from one particular plating factory, right? Or mercury in water systems, or lead in soils and dust. Well, a number of us are trained to figure out the sources and usually identify where it came from. But also a subset of us are focused on, okay, how does that source of bad stuff, contaminant, how does that move around, and how does that actually go from a geological material, water, dust, soil, to a human layer, right? So that's the net exposure. And some of these things end up amplifying. And then how does it go from an exposure potential to actually the net health burden? And in this case, zinc, it might have very high concentrations, but near industrial facilities, there's not necessarily a lot of people who are coming in contact with those particulates, and the health burden is low. On the flip side, mercury might have actually by concentration a very low environmental contamination, but of course through bioamplification and biomagnification, it becomes quite dangerous. Or in the middle ground, lead might be exposed largely where the main sources are, the soil and the dust, but there might be particularly vulnerable populations among that subset. So it really takes, so this is just another way of seeing that distance between health and environment, but kind of adding at least some middle steps to this, to that spectrum, so that we can understand that we need to understand not only the sources and current repositories of contamination, whether they be in soil, dust, or water, but if and how they're moving through the environment, and if and how they're impacting human health, right? And it seems complicated, but it's actually not. If we design systems to train scholars and to reward them, I think we can achieve some of this. To step back just briefly, of course, geohealth is a word that's all over the place now. I know that I am a longtime member of the Geological Society of America, and there is also sort of a geohealth section in there. And I was chair of that a long time ago, called Geology and Health. But I think AGU, the American Geophysical Union, has really solidified this concept. First through a journal, of course, GeoHealth Journal, which has been around since 2017. And second, as a section within AGU. And the section has expanded exponentially, quite literally, clearly tapping into an interest among the earth scientists who are involved in that organization to understand a little bit more about how earth and human health intersect with each other. GeoHealth has been nationally recognized by the American Association of Publishers as a sort of groundbreaking new format for presenting science. It won 2 prose awards, in fact, a couple of years ago. And it continues with extreme growth also in terms of submissions, in terms of now we have an impact factor and it's quite high, and in terms of interest. There's a number of examples of, I just picked this out of the recent table of contents of GeoHealth, but there's a number of examples of topics, the span of topics. And again, they touch on this intersection between environment and human health. Several of these are ones that sit pretty squarely in the international climate justice issues, like climate change and air quality, as well as mining legacies. Others in the U.S. national justice issues, for example, vulnerability of chemical facilities on coastal areas and its relation to its potential to impact lower income communities there who have very little ways to counteract that impact. But you'll see that there's a pretty broad range of things that we publish in GeoHealth. Now, I want to frame these, and I have plenty of time for questions or maybe even comments in the end, but I want to frame some of this concept of GeoHealth into some more discrete examples than the theoretical ones I've been presenting. But first, what is actually the field of GeoHealth? Well, as I mentioned early on, we're inventing it. This workshop is helping define GeoHealth in the framework of particularly maybe water, but even in broader frameworks as well. And I just want to reiterate that I'm also a professor in the global health in our School of Public Health. And when they talk about environmental health, they're not talking about things most of us are trained in. Right? GeoHealth is not environmental health. If you were to do a Master's of Public Health, for example, as maybe some of you have, you do take one environment class or maybe 2, right? And that's supposed to stand in for the bulk of your understanding of environmental science and environmental processes. But on the other hand, of course, you have a tremendous amount of training in biostatistics and epidemiology. And many people who come into the field of environmental health, some of them, sure, are scientists. Many of them are not. They might be public policy people and so forth. And GeoHealth is also not environmental sciences either, right? I train people in environmental sciences all the time at the university, where we focus very strongly on air, soil, water, how it processes, how it cycles through the environment, and how these cycles maybe interchange with each other, how climate change is impacting them. But our curriculum doesn't include any epidemiological classes. Ours doesn't include, it includes geostats, but not biostats. And so there's very different things that have promulgated, right, this split in this sweet spot in the middle, which is geohealth. And we really need to have an open dialogue about how to bring that back together again in some form or other. And I do want to frame this on equity. This is my personal, most of my research has to do with environmental justice. And I just want to remind everyone here that Flint does not exist in isolation, right? There's a lot of different triggers. Before Flint, there was Washington, D.C. Water crisis. After Flint, there's Newark, New Jersey. There's latent water crises waiting for us all over the country because of our infrastructure. But the same result tends to occur, which is not that affluent communities are impacted disproportionately, but in fact, it's usually lower income communities, and they're usually brown and black communities who are impacted most. A lot of these protections are often lacking for some of these communities, and they certainly are lagging behind science. I think we're going to see several talks during these next couple of days with emerging contaminants, for example, where the science is starting to tell us that some of these things should be regulated. Well, PFAS is one example, but is the regulation adequate in there? No, it's not. And of course, overriding a lot of this, and it's going to be the topic of these next couple of days, of course, climate change, not only reflecting on how it impacts water supplies and water quality here in this country, but of course, internationally, and how that climate change is tending already to exacerbate inequalities in communities, health inequalities. And left unchecked, it will continue to do so, right? And again, equity does not mean everyone gets the same size bench, right? We need to put our hands on the lever of equity to promote better outcomes and more resilient communities. Now, to the actual tangible examples, right? This is we're going to see this, I think, from several speakers, including my colleague Les Hakim later on. But this is a well in Bangladesh, right? Where and I lived as a Peace Corps volunteer in a country where this was the only way we got water, right? A lot of the world still gets water from wells, and most of these wells are completely unregulated. And without the science behind them, as we found out from Bangladesh and some of the arsenic issues that have come up there, we're not able to protect community health very well. And so in climate change will, if anything, exacerbate our demands on water and new water sources. And unless we're ahead of protecting communities, it very well might be that their water sources are similarly contaminated, leading to bad health outcomes. But of course, I think for every international example, one could give an example right here in the US of well water. And in fact, I think it goes, we don't really recognize this or acknowledge this, I don't think enough, but about 13% of us drink water that is on unregulated private wells. No idea what the water quality is in these, right? My colleague, Jackie Gibson from Indiana University, formerly at UNC Chapel Hill, in some recent studies showed that of these 42.5 million people, about 1/4 of them are drinking water that has unsafe levels of lead. And that proportion is, there's about 2 to 3 times to 1 proportion of lower income communities who are drinking that unsafe water versus higher income communities. Largely, of course, because of probably the water infrastructure. But nevertheless, this is a vulnerability right here in the US that has to be acknowledged and dealt with. The Flint water crisis has us really looking very carefully, and hence Biden's massive infrastructure bill has a significant amount of money devoted entirely to identifying and repairing or replacing our lead pipe infrastructure. Because as I alluded to earlier, there's Flints waiting to happen all over this country unless we are very vigilant in the short term. And then of course, in the long term, replace this aging, dangerous water infrastructure. that's lurking in many places, including my home. This is my basement water pipe. My home is from 1915. No surprise, it has a lead water intake. Right? That was very common in homes from about particularly the 20s to 40s, but nevertheless is lurking out there. There's other issues that go beyond just drinking water that have some intersection with drinking water, and of course that's contamination by fecal coliform and other contaminants in a lot of our waterways. Some waterways are, maybe not in the US, but in many places of the world, they are actually used. They pump up from rivers and streams to get their drinking water. And some of these pathogens are present, many of them in many cities throughout the US. And the situation is even more dire internationally in a lot of these areas. And climate change is also working against us in terms of fecal coliform. Particularly, I'll reflect on my own city of Indianapolis, which it's experiencing a little bit more rain. This is based on historical records, a little bit more rain, but about a 16% increase in extreme rainfall events, which is causing a lot of our storm sewers to unleash and bring raw sewage into our waterways. Climate change models show that we're going to add another 16% on top of that, and then by 2050. We are trying to work pretty hard at solving some of these problems. This is our citizen science program, at least on one component, which is environmental exposure, meaning air, water, and soil to heavy metals, where we try to find solutions for citizens through a citizen science program. It's called Map My Environment. But there's other such programs where academics are strongly engaging with communities. And here is effectively my call to action. One of them is a mantra that I give all the time, and it might be preaching to the choir here in this group, but there's a long tradition of universities doing research on communities and publishing their findings in journals and leaving the community high and dry. We need to change that tradition. Many are already, but we also, in order to put in the hard work as a let's say a junior faculty member, an assistant professor who needs to get tenure, they need to publish in papers and journals, but they also need to be mindful of the needs of the communities. So they need to also translate that research into community scale recommendations. So we also need to change the academic reward structure. My university is doing this to some extent, but it's tough and it'll need a lot more work. The second point is one I mentioned earlier, is putting a hand on the equity scale. In order to achieve equity, you actually have to disproportionately provide resources for those who are currently underserved. And finally, this last bit, which is we need to figure out a better way to train and fund the next generation. I mean, you can train them all you want, but if they're not getting grants, well, then that was a wasted effort. So I think we need to figure out ways, I say blow up, maybe I'm being dramatic here, but we need to consider our traditional graduate model, particularly as it pertains to important fields like geohealth. And in fact, implicitly include opportunities for students to engage with the community, whether that's community groups or whether that's state or local government. And even consider a med school option, right? Where students actually take rotations through different, I know this happens in some programs that aren't medical school based, but I think that our training model can be revamped to better serve the society in general. But similarly, then our funding model has to be revamped to serve those that we've now just spent all this time training in creative ways. And there's not much in the way of collaborative funding between the sectors that control our environment and our health. There are some, but there certainly is room for more. So I am very excited. I'm just sort of the kickoff. I'm the talking head to really talk about the real stuff, the really exciting stuff coming in the next couple of days. We're going to hear about drinking water and chronic exposures, a number of topics that I frame as environmental justice. Maybe the speakers wouldn't necessarily put them squarely in that bin, but I'm the first talk, so I have the liberty of doing that, where we're going to hear about a number of these issues, and as well as citizen science and public health. And finally, of course, one of the existential threats of our time are climate change and water resources. And from my selfish side, you're in good hands on a lot of this stuff. You have people who are Abner Vengosh, Alex Van Geen, of course, Antar Jutla, who are all deeply embedded in the geohealth community, who will be guiding us over the next couple of days. But with that, I do encourage you to consider what I've said. And if you want to visit our citizen science site, it's pretty simple, mapmyenvironment.com. And please don't hesitate to reach out to me, email or Twitter at those handles. And with that, I'll leave that up for a second longer. I'm going to go ahead and stop sharing the screen. And Catherine, I'll turn it over to you to moderate questions, or we can just have a conversation.
I remembered to unmute myself. So thank you so much, Gabe, for that really wonderful overview of what's going on and where we need to be. Right now, we have 4 minutes for some questions. I'm happy to moderate through the chat box, or feel free, anybody, to please just unmute yourself and shout out a question. So, and I do have one, Gabe, which is, what's the intersection then between GeoHealth and the One Health system that's also now currently under development at a global level as well?
That's right. And I've had a lot of conversations with One Health people. And my personal view is One Health is a little bit more health centric, right? Human health centric. So their circle is dealing with health systems, health access, as well as some of the environmental pressures and human health. And so, whereas I don't see GeoHealth having a lot of say in health access or health funding and so forth, that's really where One Health resides. So I consider this an amazingly productive, actually, Venn diagram of overlaps. So there is this overlap in the middle in a really positive way, I think. And so that's how I define the differences. And that's kind of backed up in my conversations with a lot of One Health folks.
I really like that idea of the Venn diagram that focuses on all of these intersections. So thank you for that. Any questions in the chat, elsewhere? Or do we want to wait until we go into the breakout rooms? Other thoughts? So
I have a quick question.
Yeah, sure.
It's a quick question. This is Dan Snow at the University of Nebraska. I really enjoyed your presentation. I've asked this before, and I always kind of think this is a philosophical question, but why do we find that quantity tends to overrule quality in terms of water resources? Very often people will fight tooth and nail over quantity issues and give very little thought or time and effort towards understanding water quality issues.
Well, thanks, Dan. That is kind of philosophical in a sense, right? It probably depends also very much on where you are, right? In the West, you might be facing, maybe just your most pressing issue decade by decade. It happens to be just simply quantity. But I couldn't agree with you more. If you look at a lot of international examples where so in the US, the quantity and quality issues can be controlled to some extent, right? We have ability to transport water here and there. We have ability to regulate, to detect whether there's problems in the water and regulate that. But boy, in the overseas, when you're in an international context that has fewer resources, you're really having to deal with both of them. And in fact, overseas, I'd say water quality tends to trump water quantity in a lot of these cases. But yeah, I like the philosophical bent to your question. I think it might very well depend on what population you're asking that question for. And Lex has a comment for us. Yeah, that's a good point.
Yeah. Lack of water quantity, you notice. Poor chemistry is often not detected. This is exactly, as I've watched several pictures of Lake Mead and Folsom Lake and a number of the different water resources in the West get in the news, right? It's very easy for, I think, the public to imagine quantity, right? You see floods or you see drought, you see trees drying up, but you don't see the chemicals that are in the water. So it's, I think, just, again, that maybe comes back to the education and outreach we need to do both to the general public and the health community. So very good point. Thank you, Dan. All right, with that, I think we'll move on to Dr. Ward's talk. And we'll look forward to coming back in about 25 minutes to the group. Thank you.
Hey, thank you. Let me just share my screen. Here we go. Can everyone see that? Can everyone hear me?
I believe so. We hear you and we see your screen.
Okay, great. Well, thank you very much for the invitation. As you mentioned at the beginning, I am an occupational environmental epidemiologist at the National Cancer Institute and have spent the majority of my career working on drinking water contaminants and cancer. But today I'll be giving a broader overview on the health effects of nitrate in drinking water, including some of our studies of cancer. Nitrate, as you know, is a very common contaminant of drinking water. And oops, here we go. So this is just an overview of my talk today. I'll be talking a little bit about the biologic effects of ingestion of nitrate through drinking water, and just very briefly on diet, because that's also can be an important source. The mechanism by which we think nitrate has adverse health effects is primarily through formation of nitroso compounds, which are carcinogens as well as teratogens. So I'll be covering these major health effects: methemoglobinemia, which is what the regulatory limit for nitrate in public water supplies is based on, as well as adverse reproductive outcomes, cancer, and then finally thyroid disease. And I will be giving some examples of how we worked with mostly hydrogeologists in our collaborations for estimating nitrate levels in groundwater. So nitrate is mostly a problem in agricultural areas. The major sources are nitrogen fertilizers, as well as animal and human waste. And as I mentioned, the regulatory limit was based on methemoglobinemia. That is 10 milligrams of nitrate nitrogen in the United States, which is roughly equivalent to the EU regulatory guideline, which is 50 milligrams as nitrate, the ion. So the highest exposures are those living in agricultural areas. And as you can see in this map to the right, produced by the US Geologic Survey, these show various watersheds across the country, and the areas in purple and red are areas where there's a high probability that nitrate in groundwater is greater than 4 milligrams per liter. So these residents, both on public and private wells, have the highest exposures, like in the Corn Belt in Eastern Washington, Central Valley of California. But really the highest exposures typically occur among those using private wells, which are not regulated, and there's sparse measurement data. So I said I'd briefly mentioned dietary nitrate. It's also an important source because certain vegetables concentrate nitrate, the parts that we eat at any rate. That's green leafy vegetables, celery and beets, for example. But these vegetables also contain vitamin C, polyphenols, and other antioxidants that inhibit the formation of nitroso compounds. So nitrate itself is not carcinogen or teratogen. It's only through the formation of these nitroso compounds that it can exert negative health effects. Nitrate ingestion can also have beneficial effects on the cardiovascular system through the formation of nitric oxide. And that has been shown to, for example, decrease blood pressure. But recently there's been, and you may have heard about supplements with very high nitrate levels in the grams per liter range, like beet juice supplements that are taken for athletic performance. And there's a recent study that showed indeed that these supplement use can cause nitroso compound formation. So in spite of the good things along that come with nitrate in beet juice, these very high levels are probably not safe. And you also probably have heard about nitrate and nitrite added in the curing or processing of meats. And that has consistent, I'm not really going to be talking about that today because we're talking about drinking water, but that has consistently, this form of nitrate cured meats has been linked to colorectal cancers as well as some other cancers. So this schematic here just kind of shows the way that ingested nitrate is taken up in the body through drinking water or diet. And then the oral bacteria in the mouth reduce nitrate to nitrite, which is a very reactive compound, which is then swallowed, reacts with stomach acid to form nitrosating agents that react with amines and amides. And think about proteins in your diet, and also certain drugs have amine and amide groups that can be nitrosated to form these large number of nitroso compounds. And this process is increased in the presence of heme iron, like red meat or thiocyanate from smoking, and decreased in the presence of antioxidants like vitamin C, which is why normal levels of dietary nitrate don't form a lot of nitroso compounds in the body. So again, a little background on some of the human studies that have looked at nitrate ingestion and have shown a direct relationship between nitrate conversion to nitrite, which again happens in the mouth. And this graph shows a range of percent reduction of nitrate to nitrite from 10 to 30%. And as you can see, as the percent of nitrate reduced to nitrite, the very active compound, as that increases the excretion of nitroso compounds in urine. So again, these were human feeding studies that demonstrated this quite a few decades ago. And overall, a lot of the nitrate we take in the form of water or diet is excreted in our urine, but overall about 5 to 8% that's ingested is reduced to nitrite by the oral bacteria. So a number of studies have looked at people drinking normal levels of nitrate in their water supplies. And a couple of studies, one in the US and one in Denmark, looked at people drinking wells that had nitrate above the regulatory limit and saw that there was an increase in endogenous formation of nitroso compounds, again measured in urine. But a Canadian study where levels were all below 5 milligrams per liter, half the MCL, found no increase in nitroso compound formation. So again, these are a class of compounds that include nitrosamines and nitrosamides and have been linked to cancer and birth defects. There's over 300 nitroso compounds that have been tested in animals. About 90% were carcinogenic. These are carcinogens in 39 animal species, every animal species that's been tested, including non-human primates. So it's unlikely that humans are not susceptible to the carcinogenic effects of nitroso compounds. And they cause tumors in multiple organ sites, including in the digestive tract, the urinary tract, and other sites throughout the body. So the in utero exposure can also cause congenital malformations, especially of the central nervous system. So this is kind of a summary of what we know based on the animal data. And in particular, first trimester exposures are particularly important. So moving to the really the epidemiology or the health studies in humans, I wanted to start with methemoglobinemia or blue baby syndrome. It was in 1945 in an article in JAMA that really brought this problem to the attention, at least in the United States, the attention of the health community. A pediatrician reported cyanosis in several infants in Iowa that were bottle fed with formula made with high nitrate well water. So nitrite, which is nitrate converted to nitrite, binds to hemoglobin and forms methemoglobin, and the health effects are apparent when about greater than 20% of the hemoglobin is in methemoglobin form. And infants less than 6 months are most susceptible. So there was a later investigation of almost 300 cases across 14 US states, and they found no cases below 20 milligrams per liter. So the regulatory limit was set at half of that at 10 milligrams per liter nitrate as nitrogen. So it's been that case for a long time. And some of the agricultural states in the Midwest in particular have measurements of nitrate in drinking water going back quite a few decades, even before the Safe Drinking Water Act, because of this concern about blue baby syndrome. More recently, there was a report in the literature of a case in Wisconsin at about 27 milligrams per liter nitrate nitrogen. So not much higher, less than 3 times higher than the regulatory limit. But there've been very few reported cases and none that I have found since then. But nitrate or methemoglobinemia due to nitrate contamination of drinking water is an ongoing public health problem, particularly in Eastern Europe, the Gaza Strip, and Morocco. So turning now to adverse reproductive outcomes. I'm going to talk mostly about the studies of spontaneous abortion and congenital malformations or birth defects. There's really been very few studies of other outcomes, such as low birth weight or preterm birth. So we know from the reports in the animal literature that high maternal methemoglobin levels can cause abortions, both in lab animals as well as it's been reported in livestock. In 1996, there was a CDC MMWR report of a cluster of spontaneous abortions in women in rural Indiana. And these were women who were on private wells that had levels of a little greater than 20 milligrams per liter nitrate nitrogen. When the women switched to low nitrate water, they had healthy live births. And one of the women had a healthy live birth when she was previously on a well that had lower nitrate levels. So this was somewhat circumstantial evidence, but fairly compelling that at least high nitrate water above the regulatory limit may increase risk of spontaneous abortion or miscarriage. In contrast, there was a study in Massachusetts where there was no association with levels with spontaneous abortion when nitrate levels were below 5.5 milligrams per liter, which they were for the entire study population. So then moving on to the studies of adverse reproductive outcomes, which had mostly focused on central nervous system malformations. There's been 6 studies in a number of countries: Australia, Canada, California, Texas, and then another study that occurred in Texas and Iowa, and one more Canadian study. So 5 of these 6 studies saw a relationship between nitrate levels in drinking water and at least one central nervous system malformation. I'm just going to tell you a little bit more about the more recent studies by Jean Brender. The first study in Texas found a 2-fold increase in neural tube defects, and the highest risk was for women who had high nitrate in the drinking water and who also took prescription or over-the-counter drugs that can form nitroso compounds in the body. So these nitrosable drugs, in combination with higher nitrate levels in the drinking water, resulted in the highest risks of neural tube defects in this study population. She then conducted a larger study that expanded also to Iowa and found a 2-fold increased risk in various specific neural tube defects. And again, the highest risk was for women with high total nitrate intake, taking account their dietary as well as their drinking water intake and nitrosatable drug use during the pregnancy. So in summary then, 5 of the 6 studies that have been conducted of these central nervous system malformations have seen positive associations of nitrate concentrations in the drinking water, and the levels were less than the regulatory limit in 4 of the studies. Okay, so then turning to my area of study for cancer. In 2006, the International Agency for Research on Cancer, which is part of WHO, reviewed the evidence for ingested nitrate and nitrite in relation to cancer. And this expert panel concluded that ingested nitrate and nitrite were probably carcinogenic to humans when they were ingested under conditions favorable for the endogenous nitrisation, which is another way of saying for the formation of N-nitroso compounds. So the way the IARC evaluation works, it considers the data from animal studies, and that was considered very strong based on what I talked about before, and human mechanistic studies, and I showed you one of those in terms of the relationship between the percent of nitrate converted to nitrite and nitroso compound excretion, and the direct relationship with ingestion and nitroso compound excretion. But in terms of the epidemiology studies, it was dietary nitrate was evaluated separately from drinking water nitrate, and there were no studies that showed increased risk with higher dietary nitrate intakes, which was reassuring because those are mostly fruits and vegetables, which we know are generally very good for you and protective against cancer risk. But for the drinking water nitrate studies, it was considered that the evidence was inadequate. And that was because there were few studies of specific cancer types. The exposures tended to be lower, below the regulatory limit, because the population studied were using almost exclusively public water supplies. And historical exposures hadn't always been evaluated, and factors that affected N-nitroso compound formation were not always considered. So I just want to briefly, there's quite a body of literature, and at the end I'll show you some references that include all these studies I'm mentioning here, but just give you a brief overview of the results of case control and cohort studies. So these are studies where exposure to nitrate in drinking water is estimated for individuals. And these is a summary of cancer sites where there's been at least 2 studies. So I'm showing you on the left the cancer site, and then in parentheses, the total number of studies, and then parentheses, the number that were positive, showed a positive relationship with drinking water nitrate in at least one subgroup. So the strongest evidence to date is for colorectal cancer. 4 out of the 5 studies that have been conducted have shown relationship with risk. And there's been recently a couple additional studies of childhood brain tumors. And so that has actually meant that 4 out of the 4 studies to date have shown some positive association, again, in some subgroup or for some histologic type of childhood brain tumor. Other sites that have been studied include bladder, kidney, non-Hodgkin's lymphoma, pancreatic cancer, and adult brain cancer. And as you can see, there's really less evidence for those sites, but not a lot of studies. So I'm going to talk about where some of this evidence comes from in a little more detail. It's been unfortunate, but until really the last 10 or 20 years, there haven't been many studies that asked about drinking water source in terms of epidemiology studies. There have been some specific studies looking at disinfection byproducts or nitrate case control studies where you focus on one particular cancer site. But cohort studies really represent a great opportunity to look at a number of different cancers. And for nitrate, hopefully you've gotten the impression that that's important to do because there's potentially a lot of cancer sites could be related to risk. So this cohort is a cohort of older women in Iowa. 73% use public water supplies, 25% private wells. They asked this question on just right after enrollment in 1989. And so for this study population, we were able to link the public water supply monitoring data, which, as I mentioned, goes back quite a ways for nitrate, as well as trihalometane regulatory data, to the women's address. If they said they used a public water supply, we linked to their utility, mostly by city name. And then we knew the duration that they had used that water source based on the questionnaire, and we were able to compute metrics of exposure like the average nitrate level over the period they lived there, as well as the years they lived with at a water supply that had levels greater than half the maximum contaminant level. And this was a very stable population. 82% had used the water supply for 16 or more years. So just to give you a flavor of, again, some of the details of how we go about doing these studies and where these data came from. So in an early follow-up of this cohort, there was an increased risk of ovarian cancer for women using public water supplies and suggestion for women using private wells, and similarly for bladder cancer, a significantly increased risk, but no association for colon, rectum, lung, and these other sites. We did an update of this cohort, and after additional over 20 years of follow-up with a lot more cases, and we saw a similar increased risk of ovarian and bladder cancer, as well as we did updated results for these other sites and saw similar results, no association. We did find an increased risk of kidney cancer in the highest exposure group, which hadn't been seen in the first follow-up. We accounted for trihalomethanes, which were moderately correlated with nitrate, and we looked at factors affecting nitrosive compound formation. So just some results for ovarian cancer. I think this is really interesting. We saw an increasing risk with increasing average levels in the public water supply. And there was also an elevated risk, marginally significant for those using private wells compared to those with the lowest quartile of average nitrate levels in their public supplies. And we looked at the group who had higher vitamin C intake as well as lower vitamin C intake. The women who had higher vitamin C intake above the median had no elevated risk. All the risk was occurring in women who had lower vitamin C intake. So again, sort of fitting with the subgroup who would be expected to have higher nitrosive compound formation. So this is the kind of study designs we really need to really get at whether nitrate in drinking water is risk factor for cancer. And all these women on public supplies were using nitrate below the regulatory limit. So again, I mentioned the most consistent evidence is for colorectal cancer and now for childhood brain tumors with a couple of recent studies. There's still few studies of specific cancer sites. And the limitations of most studies are that people using private wells who we know have the highest exposure are usually not considered, or they're considered lumped together as a group because we don't have measurement data to characterize their exposure. So this is where it's an important, and I'll get to an example here shortly on how working with geologists and doing geohealth can really improve our studies. So the final health outcome I wanted to talk about was thyroid disease. And here it's a little bit different in that nitrate directly inhibits iodide uptake by the thyroid, which can result in thyroid hypertrophy and hypothyroidism. There's been a few studies looking at nitrate in drinking water and hypothyroidism. A study in children found that subclinical hypothyroidism measured by ultrasound was increased in Slovakia among children with higher nitrate in their drinking water. In the Iowa Women's Health study that I talked about, we saw that higher nitrate ingestion, summing together both dietary and drinking water sources, was associated with a higher prevalence of hypothyroidism reported by the women. And then this study, I'll just show you a couple of slides, a cohort of older Amish men and women in Pennsylvania. We saw an association with higher nitrate levels estimated for private wells and subclinical hypothyroidism, but this occurred in women, but not men. So in this study, which was in southeastern Pennsylvania, 3 counties in southeastern Pennsylvania, we worked with a hydrogeologist. Actually, it was someone from the U.S. Geologic Survey who had seen some of our studies and called me up and said, we have all these nitrate measurements. I'm interested in trying to do something with it. So we had over 3,000 measurements, and we developed a model using some of the variables you see here on land use, carbonate formations, karst density, and aquifer information. So we developed a predictive model for nitrate in groundwater, which we assumed was related to their exposure through private wells. And then these are the results. We saw that we looked at clinical hypothyroidism defined using thyroid stimulating hormones as levels as the cut point, and we looked at subclinical hypothyroidism and saw a significant increased risk for women who had higher nitrate levels greater than 6.5 milligrams per liter, although there wasn't a clear dose response. There was no association in men. So just some quickly some information about our ongoing research on drinking water contaminants in the agricultural health study cohort. This is a NCI and NIEHS, as well as EPA collaborative cohort of pesticide applicators and their spouses in Iowa and North Carolina. It's over 90,000 participants. 70% used private wells at the time of the enrollment in the mid-90s. And we estimated nitrate in private wells using random forest models. And I'll just show you an example shortly. We also linked participants who said they used public supplies to the Safe Drinking Water Act measurement data for nitrate and disinfection byproducts. And we estimated dietary nitrate and nitrate from food frequency questionnaires. So this shows you some of the factors that went into the most significant factors that went into the predictive model for nitrate in private wells. Here we really had to do something. We have limited measurement data for the actual cohort, but we did have over 30,000 measurements with information on well depth over a couple decade period that we used. We collaborated with Tom Nolan from the US Geologic Survey to develop this model, and also with David Wheeler at Virginia Commonwealth University, who's a spatial statistician. So we divided the data set into a testing and training set. We evaluated over 150 variables, including land use, as you see here, the location of animal feeding operations, which is shown here, and karst geology, which turned out to be very important. So this shows our predicted nitrate measurements for Iowa, and you can see there's quite a different spatial pattern, and that varied by well depth. The top figure shows wells less than 100 feet, the bottom deeper wells greater than or equal to 100 feet. And 30% of the cohort is estimated to have exposure over 10 milligrams per liter. So you can see it's actually this area in northeastern Iowa where there's a lot of karst geology that had highest nitrate levels for deeper wells. So we developed a similar model for North Carolina, and we're evaluating risk of cancer and thyroid disease. That work is ongoing. So I know I'm just about out of time, but I wanted to just end with a few thoughts in terms of what needs to be done in the future to clarify the relationship between nitrate ingestion and nitrosocom and cancer and other health outcomes. I think we really need to clarify that relationship with nitroso compound formation below the MCL, and more controlled studies are particularly important, and particularly characterizing the role of the oral microbiome, which is now feasible to do. That could be incorporated into future epidemiologic studies. We certainly need more studies in populations with high exposures, particularly those using private wells, but also smaller public water supplies, which have been shown to have higher nitrate levels. And there's certainly inequality in these exposures. That's been demonstrated in a nice study in California showing that the Latino population in California is more likely to have high nitrate exposures through their drinking water. And exposures are increasing and certainly will be exacerbated by climate change. And I'll leave the experts later in this conference to really talk about how that may come about. With that, I would like to end by thanking some of my collaborators who are collaborators on the work I showed here today. And then I'll end with a couple of reviews that we did over the most recently in 2018, that described in much more detail the health effects that I talked about today. So thank you for your attention, and I'll stop sharing my screen.
All right, we have time for maybe one question before we move on, but we really can have more questions during the breakout room. Crystal, did you have a question?
I do. Crystal Powers, University of Nebraska. Just wanted to get your thought on another philosophical question, because it was an excellent presentation. Thank you. One of the best I've heard on the overall effects. At what point have we done enough studies to say we need to get information into people's hands so that, you know, they can get safe drinking water? I know it would kind of torpedo our cohort studies, but some of this seems fairly compelling.
Thanks. Yeah, I mean, I think some, you know, regulation of private wells is left up to the states, and some states do a better job than others in terms of educating their population on private wells. And I think they do generally a pretty good job of making people aware of concerns for pregnant women and for infants. But I think, you know, if you kind of follow the precautionary principle, you might want to consider that, you know, the evidence is increasing for some cancer sites, for certainly adverse reproductive outcomes. You know, if pregnant women are being careful, they're probably protected. But these concerns, and even things like thyroid disease, which is very treatable, but not something, you know, you want to develop. So I think making that aware, making the public aware that there's a broader range of health effects other than just methemoglobinemia is important. And the word seems to be getting out there, but it maybe isn't consistent because each state kind of does it their own way. And I think hand in hand with that, though, really has to go some support for private well testing, because if you don't know, I mean, nitrate is tasteless, odorless. You wouldn't know it was there unless you test. So Iowa does a really great job of that. They've had a grants to counties program, which is why they have so many private well measurements that are available, but other states, not as much. So yeah, those are a couple of thoughts.
All right, well, we'll come back to this in the discussion group. And I also have a question kind of related to that precautionary principle, and when is weight of evidence enough? That's something that really I think can be dug into more a bit later. But thank you, Dr. Ward, so much for that very interesting and provocative talk, because I think it'll lead to a lot of discussion. With that, I'd like to introduce Dr. Avner Vengosh as our next speaker. Dr. Vengosh.
Thank you. Can you hear me well?
We hear you.
Okay, great.
And we see your talk right now. It isn't in presentation mode. There you go.
Yep. So thank you, Catherine, for inviting me and all the group. I just lost my electricity and it came back just in time. So I'm glad to be here and talk to you about some of our research about chronic exposure to naturally occurring contaminants in drinking water. First, I would like to introduce my group at Duke University, the PhD student who've been involved in different parts of the study that I was involved. Some of the names will be repeated here. So as we know, and then we heard before, we all talk a lot about water quantity and much less about water quality. And basically many of the global assessments are based on available water and the balance between water availability. And that map is actually misleading, because if you look at many parts of the world, you think you have enough water, but the quality of the water is insufficient for human consumption. In many cases, also agriculture consumption, which is the major resource for groundwater is a major resource for agriculture. And therefore, we really don't see the magnitude of water scarcity because we are focusing on water quantity. So the comment made before is extremely important. And we see this vicious circle when we talk about global change and the dynamic between overexploitation and global warming that are changing how it's kind of more water we use, more water stress, and then more water quality degradation. And I think that's something that is kind of the future research that need to further, and I'm going to highlight some of the points, but I think this is only the beginning understanding at the magnitude of how water quality degradation is enhanced by changes on both our action of overuse of water resources and global warming. And of course, when we talk about water quality, there are the major suspects, so to speak. There are wastewater, which is a global affecting everywhere, agriculture return flow that affecting salinity and nitrogen that we just heard. Industry, energy is a major source of water quality issues, which deserve another talk, which my group has been engaged very extensively. But today I want to focus on the naturally occurring geogenic contaminants in groundwater resources that have some silence effect, or as people call it, the silent tsunami, that affect human health more than we actually imagine. And much of the focus that I understand going to talk tomorrow is about arsenic. So I'm not going to talk about arsenic at all, but I'm going to talk about other agents of natural occurring contaminants that affecting human health, including uranium, radium, and hexavalent chromium, which may be surprise to some of you. It is a natural occurring contaminant and not what we learn in the movies from in the 80s or whatever. So all those natural occurring contaminants affecting vulnerable population that don't have any means and ability to protect themselves from those geogenic contaminants in their drinking water source. And the more study we're conducting, the more realization we have that the occurrence and the prevalence of those contaminants is much wider than we think and we thought before, and we keep discovering their occurrence in different parts of the world. There is the issues of arsenic that I mentioned. There is the issue of fluoride that is also a global phenomena that affect the millions of people. And I'm not going to discuss this today. I'm going to focus on several elements that I think deserve more attention. One of them would be uranium, that uranium would have a health effect. Specifically, the toxicity of uranium would cause kidney disease, and several studies have shown that elevated uranium in water associated with different types of kidney diseases. And the interesting about uranium that it is only the chemistry of the water is the key parameter for actually finding uranium in water. It will find it highly soluble when in under oxic condition, and specifically when it's attached to other chemical molecular like carbonate in the water that generate this uranium speciation that make it more soluble, whereas under reduced condition or low pH, uranium becoming insoluble in the water. So we see this distinction, that the chemistry showed the distinction between solubility under oxic and being insoluble under anoxic condition. And we go back to that because we're going to show you that changes in the water chemistry induced from climate change and operation would change the dynamic of the water chemistry and therefore also the occurrence of uranium. We are writing now a review paper on the uranium and other radionuclide occurrence in groundwater, and we made this map to show that the Western United States have a large spectrum of occurrence of uranium exceeding the drinking water standard made or guidelines made by the World Health Organization, which is the maximum contaminant level in the US of 30 parts per billion. And some aquifers have much higher abundance of elevated uranium. like in the Central California or the High Plain Aquifer. And several studies demonstrating that in the US, it's associated with agriculture activities. A recent study that we in a group at Duke University conducted in India suggests that uranium is much wider occur than we thought, and basically found that uranium is highly abundant in different parts of India in groundwater that is used mainly for drinking water and agriculture, and specifically in northwestern India, where uranium is, the abundance is really high in certain parts and certain aquifers that having high elevated level above 30 parts per billion, specifically state like Rajasthan and Punjab with the high concentration. And we see that the high concentration across different aquifer types, different lithology, different rocks, you can see different occurrence of uranium. But most common feature is having the association of uranium with bicarbonate due to affiliation or association of uranium with carbonate. And basically, alkalinity of the water is the key for the occurrence of uranium in the water. And if you understand why there is alkalinity in the water, you can actually predict pretty well what will be the occurrence and concentration of uranium in the water. And in a place like India, they don't have the capacity, analytical capacity for measuring uranium. Measuring alkalinity, which is much more low-tech capability, could be a very good predicting tool to enable a state agency to evaluate uranium occurrence once you're building this calibration. And I think that will lead us perhaps what Gabe was talking about, citizen science, and how us as a scientist, important to build the infrastructure to allow citizen science to be correct. Because citizen science could be really misleading in some cases. So it's very important to be able to build it correctly, and we can discuss it later later on. So what we kind of find from our study in India and many other studies, that we have integrated off condition of factors that will allow uranium in groundwater. You need the lithology, the source of uranium in the rocks. You need the alkalinity control, and there are different mechanisms, geochemical mechanisms that control alkalinity, and of course, oxidation of the water, which by itself being triggered by irrigation, eutrophication process coming from agriculture, and groundwater drawdown itself, which trigger oxidation of the groundwater. So together, you get this uranium in groundwater. Another important source of contamination is those radionuclide that coming from the decay of uranium. And some of them are, in addition to uranium, are radium and radon that you probably know affecting lung cancer, whereas radium would be associated with bone cancer. And radium, which one would think it's very rare, it's actually much more common than we think. Many studies have showed that elevated exposure to elevated radium in water is associated with different types of leukemia and bone cancer in the exposed population. And there are very solid epidemiological data built on that. And in some groundwater, like the Middle East, for example, millions of people exposed to water, groundwater, which is the only water available in those countries, in Egypt, in Saudi Arabia, in Jordan, and southern part of Israel, where the sandstone aquifer contain elevated level of radium that put them at risk upon consuming this water. An early study we published in 2008, working in Jordan, revealed this is one of the important aquifer in the Saudi Arabia and Jordan. In fact, the only fresh water available, fossil and fresh water. So this is old water that was recharged thousands of years ago and preserved as clean water, fresh water. However, it has also elevated level of radium, really much higher than the drinking water maximum contaminant level, and putting the people in those countries at risk that are using this water. And the issues that we are finding is the more the aquifer is clean, the more higher permeability, clean quartz sediments of the aquifer, the higher the radium would be, because there are no secondary mineral that retain radium like would be in other places. So the best aquifers in the Middle East, and it's not only the Middle East, it's also United States, the best sandstone aquifer that you could be ideal for drinking would have elevated level of radium, which is extremely carcinogenic element. And this is kind of the map of those fossil groundwater that affecting millions of people across the Middle East. And we are now discovering that in central Texas, in a city, small town like Brady, they are consuming water that is much, much higher than the maximum contaminant level allowed in the United States. Here in 2021, we are using groundwater of Shannon, I think you need to mute. Thanks. So in the Hickory Aquifer of Central Texas, there are elevated level of radium that exceeding the drinking water level. Again, clean, fresh water coming from a sandstone aquifer with elevated level of radium. And there are many other sandstone aquifer specifically in the Western United States having that as well. And then hexavalent chromium. We all learned that hexavalent chromium came from the electricity company in somewhere in California where Erin Brockovich was working on that. And that was in the movie, but in reality, hexavalent chromium is much more abundant and much more occurring in many groundwater resources in United States and elsewhere. There's issues with hexavalent chromium because of the concept of being related to the industry contaminator. Actually, the EPA has not established a drinking water standard for hexavalent chromium drinking water. The standard that is available is 100 parts per billion for total chromium, whereas the California drinking water standard is 10 parts per billion, and the California public health goal is 0.02 parts per billion exclusively for hexavalent chromium, giving that the risk of consuming water with hexavalent chromium. So we see a gap between the regulatory of with the non-inclusion of hexavalent chromium in the drinking water regulation and the occurrence of hexavalent chromium. So hexavalent chromium would occur when under oxic conditions, similar to the uranium we saw before, whereas the trivalent uranium under reduced condition will be insoluble, similar to the uranium. And therefore, every chromium we find in water, as demonstrated in our study, would be coming as, or 95% would coming as hexavalent chromium rather than trivalent chromium. Several studies have shown that having rocks like mafic rocks, which enriched in chromium, during the weathering process of oxidation of manganese oxide will trigger the oxidation of chromium, trivalent chromium, and forming the hexavalent chromium in the groundwater that is being recharged into the aquifer. And in several studies in North Carolina, we demonstrated that hexavalent chromium is existing everywhere, and in some parts of the state in much higher concentration. We showed that some hotspot near Raleigh and Greensboro that would have elevated level that exceeding the recommended level of 0.02 parts per billion, but in the same time, much below the 100 parts per billion of the MCL drinking water standard. So we are in a gap between, for those homeowners who are having private wells, they are exposed to hexavalent chromium, but they are not really above the standard. This is kind of a major limbo. We are everywhere in this country right now. And what we found that every time you find chromium in the water, you actually measuring hexavalent chromium. And in some cases, It's exceeded even the California maximum contaminant level goal of 10, and in almost 90% of the cases exceeded the public health goals of 0.02 parts per billion. And what we build probability based on the geology and based on the occurrence. And we can see that some rocks would have higher probability of having hexavalent chromium in the local groundwater. So the geology plays a major role, but on top of that, the depth and other hydrogeological factors also play a major role, as I'm going to show you. But the also important thing that is, together with the geology, you can actually link where people actually use the groundwater. And here you see the domestic groundwater user in 2015 overlying with the high probability of having elevated level of hexavalent chromium, meaning that a large part of the population of North Carolina and basically all the southeast of United States would be exposed to relatively high concentration of hexavalent chromium. And again, by analyzing the geochemistry and the hydrogeology, we can see that there is not only mafic rock, as previously thought, we see it also in non-mafic rock. We see how the redox and the pH play important role, and this combined with the hydrogeology and depth of the well would give you the hotspot where you can actually find hexavalent chromium in drinking water. And one of the points we found that what we are measuring in North Carolina applies also all to the all Southeast United States, which has the same geology and the same aquifer composition, talking about Georgia, South Carolina, and Virginia. So it's a large population in the Southeast, especially in areas that are developing now, and especially for people with private wells in the rural and the suburban areas that are really don't know what in the water. And chromium and hexavalent chromium is not common chemical that you usually measure in your well water. Now, one of the future research is the co-occurrence of contaminants, because most of the epidemiological studies have focused on one single contaminant and its effect on human health. But what happens if you have more than one? And this is kind of an intriguing question, because we see that if you look at arsenic, uranium, vanadium, and chromium, you can see that some rocks will have higher tendency to each of those contaminants, but you could have probability of having co-occurring of those contaminants. So the co-occurring of those contaminants could induce very interesting question for epidemiological study. What would happen if you have more than one contaminant in the water? And we did this by looking at the probability of having more than one contaminant in the water. And we can see that in some cases, the same unit of rock could have co-occurrence of 4 contaminants in their drinking water for those. And when I say occurrence, it meaning that having concentration that exceeding the health guidelines, it's meaning that the homeowners, in most cases, private wells would be exposed to 4 contaminants at the same time. And the question one would ask, what does it mean for human health once you have exposure to more than one contaminant? So to kind of finalize the points that I would like to make is basically that highly toxic and carcinogenic natural occurring contaminants are highly prevalent in global groundwater resources. It's not restricted, and it's not only arsenic, no offense, everyone. It's much more occurrence as well. And I'm not underestimate arsenic. I think, but it's behind, in addition to the arsenic impact. And the chronic exposure to this geogenic contaminants in drinking water induces multiple health effects. And we've seen cancer, health diseases, kidney diseases, like I mentioned in India. And Rajasthan in India known to have the highest abundance of kidney diseases and directly associated with the elevated uranium concentration in drinking water. The point that Gabe was mentioning before, that large worldwide population, specifically the rural and the poor communities, and are most vulnerable and exposed to naturally occurring contaminants in their drinking water, in their wells, without awareness to the occurrence of these contaminants, nor the resources to build treatment capability or even adequate monitoring program to know what's in the water and how to protect the population from that. And then the future is even more problematic because we are talking about overuse and we're talking about climate change that expect to change the hydrological condition. For example, groundwater decline would change all the dynamics of geochemical condition, for example, inducing oxidation of groundwater drawdown, and therefore have increased the abundance of some of those oxyanions like uranium and vanadium and hexavalent chromium, and could increase the groundwater toxicity and impact on human health. And that's kind of the direction one should be looking. What's happened when we are changing the dynamic, the hydrogeological dynamic to those different changes, and what we knew in the past can be inflicted into the future. And with that, I would like to thank you for your attention. And I hope I didn't exceed my time.
Your timing was perfect. Thank you very much for that very informative talk, Dr. Venkash. With that, I'd like to open it up to questions. And feel free just to unmute and shout it out or put it into the chat box. I do also want to remind everybody, don't log out. Just please mute and turn off your videos and then come back at 10:45 for our breakout sessions. We'd love to hear everybody's thoughts, opinions, ideas for moving forward. All right, now that I've made those announcements, questions for Dr. Venkash.
Dr. Venkash, this is Arindam Malakar from University of Nebraska at Lincoln. I have one question. You mentioned that irrigation water can be a factor for mobilizing these trace elements. How do you think different kind of irrigation practices can impact this mobility?
Well, what we know that irrigation and specifically process that is somehow inevitable during massive irrigation, like nitrification process, would induce oxidation that has suggested to be associated with elevated uranium concentration. So we've seen it in the Central Valley in California. We've seen it in the High Plain Aquifer, and we see it in Rajasthan in areas that being irrigated extensively. Probably, if you are using much less fertilizer, which is usually farmers use excess of, and using a drip irrigation, would have much less recharge of nitrogen-rich groundwater into the unsaturated zone that would induce those oxidations. So transition from the traditional irrigation through drip irrigation would reduce the likelihood of inducing those processes.
Thank you.
Thank you. Thank you.
Dr. Van Dien, do you want to ask your question, or would you rather I did?
Sure. No. Thanks, Avner. Very interesting. I was wondering whether you could elaborate on how well this connection is between uranium and drinking water and kidney disease, because as I point out in the chat, NIH, I think, is about to spend millions of dollars in multiple countries to study kidney disease of so-called unknown origin in Latin America, in India, affecting primarily agricultural workers. And so I'm wondering about other, contributing factors as well.
So, I mean, we didn't conduct epidemiological study because I'm geochemist. As you know, so this is based on several epidemiological studies that have been conducted, and it's all case studies that demonstrated a population exposed to relatively high uranium. And I think this is being pretty well established. However, I know there was case in Sri Lanka, for example, with also areas of high prevalence of kidney disease where they didn't find it, elevated uranium. So, I'm not sure I have the answer for that. It may be there are some other oxyanions that are playing a similar role like the uranium on that. But as far as I know, it has been really well established, the link between uranium, at least in those epidemiological studies that has been reported in the literature. It could be that kidney disease could be associated with other factors as well. So we cannot rule that out. And it will be interesting maybe to hear about this NIH initiative to see if the target of what they're looking would be more, we could kind of giving more guidelines to look for example, the aquifer type, the lithology, you know, to do what Gabe was talking before, to link between the health people and the geoscience people. That could be interesting kind of exercise.
Well, and that's something I got out of your talk as well, is the importance of really having these cross-disciplinary groups work together. Hydrologists, geologists, geochemists, chemists, environmental scientists, bench scientists, health researchers, and epidemiologists as groups to really try to figure out sources and outcomes of all of these problems at these kinds of geologic scales. It fits very well within this geohealth perspective. All right, any other questions here for Dr. Vengosh before we move into the breakout rooms? All right, with that, please come back. We do want to hold a broader discussion in smaller groups and start to feel like we're coming up maybe with some solutions. So I'll see everybody. It's now 10:42 according to my clock. How about everybody, we're back by 10:50 our time, or 10 minutes before the hour, wherever you are in the world. I know we have several people here, I think from Asia and even Latin America. Okay, we'll see you all in 5.
Kathy, this is Alan, would you stay on the line? Would you stay on the line so we can, during the break? Kathy, I'm not 100% certain that I know how to get into the chat.
Into the breakout room?
Yeah, into the breakout room.
It'll come up. So Aaron, can you help?
Alan, hi. So what's going to happen is I'm going to open up the breakout rooms, which means it's going to send you an invite on your screen saying, do you want to join the breakout room? Okay. You click yes, it'll do a little spinny wheel thing, and then you'll pop up and you'll be in another Zoom room.
Okay, sounds great.
And at the end, it automatically comes up and tells you have about a minute left in the breakout room, and then it throws you over. I think we're all back. And I'm going to now officially introduce Dr. Alan Kolak. Alan, would you like to start the broader discussion with what your group then was discussing? And then we'll move around to each of us who were in a group. So you got about 10 minutes or less until we pass it to the next group.
And then Kathy, I'm happy to do that. And after that occurs, what's our next step? Then are we going to kind of, once we do that for all 3 groups, we're going to open it up to a overall conversation? Is that right?
I think that's the goal, is to come up with maybe some bigger ideas and maybe goals for next steps. Okay. Like what do we think would be a really major next step that we could start taking hold of and ask for volunteer leadership to formulate moving forward with some of these more complex issues.
Great. All right. Thanks, Kathy. And I'm gonna keep this somewhat brief. And my apologies to my breakout session colleagues if I've misinterpreted what was said. But I'm really interested in hearing from the overall group and the feedback. So I'm gonna, like I said, I'm gonna try to keep it somewhat brief. But we started off asking the question of effectively, very bluntly, who's to blame and how do you get them to pay? And from that perspective, it very quickly moved to really there's two different divergent paths, if you will, relative to water contamination as a public health concern, one being anthropogenic compounds, which would certainly be traceable, obviously, from its very nature back to a human origin. And then a second being geogenic compounds, such as what was shown earlier on today relative to trace metals and metalloids in North Carolina, where there's really no one that you can point your finger at unless it's, you know, geology itself and say you're to blame for this. So it becomes a nuanced issue fairly quickly. Second thing that we talked about was as per the, and this is going to come up perhaps tomorrow, but certainly on Wednesday, the relationship between water quality and climate change. And is that somewhere really, the question was posed, is that somewhere where we necessarily need or want to go now, given that if you're really looking through the lens of water chemistry and health, perhaps climate change is the tail wagging the dog here. And it's really not a climate change is a secondary issue relative to the issues that were discussed this morning. So that was another issue that we had. The place where I thought we made some very interesting headway, not to minimize what I've already said. The place that I thought we made some headway is that we're living in a really unusual socio-political environment right now. And that is that we have the access or the capacity to provide citizens with tools, whether those be COVID vaccination shots or whether those be arsenic strips to measure the quality of their groundwater that they're using as their drinking water supply. So we have sometimes better, sometimes worse, but we have the capacity to distribute that to large communities over broad geographies. The problem, as we all know, is, and that gets to what Gabe was talking about earlier on today relative to citizen science, and I really hope that comes up more in the next 2 days. However, that also gets to the fact of the socio-political aspects of it, which are either people don't believe the science, or people are frankly afraid that, very bluntly, declines in water quality are going to reduce the resale value of their property, so that they don't want to know, because if you know, you're going to have to disclose it, and if you disclose it, your lifelong nest egg of your household has now diminished in value. And that's although that may sound trivial, particularly when put in the context of public health, it's a very real concern. Finally, what we all came to kind of at the end, which I thought was really, in a way, the breath of fresh air, right, is citizen science very often from the perspective of environmental reconnaissance. It often works very, very well when it's the children, the youth, the pre-19-year-olds that are involved. Because while people may be reluctant to be vaccinated, they may be reluctant to test their groundwater for arsenic, they're not reluctant to put their children into the best possible positions moving forward to have the best life that they can. We all care about our children. We all care about the future generation, particularly our future generation. So that was kind of the shining light, I thought, at the end of our conversation. And with that, I'd be real interested in hearing what the other two groups discuss.
All right. So I think, Jesse, were you in charge of one of the other groups?
Yeah. So I guess, to take it from Alan, I'll just move backwards. We started off or we ended on talking about that education piece and talking about trying to figure out ways of integrating this into education so that younger generation are more aware of this, which then would potentially have ripple effects across the entire, especially when we're talking about water quality and doing water quality testing. One of the first examples that I came up with was that Dan Snow runs, which is the Know Your Well, Get to Know Your Well program that they have there. Similar programs like that would be very useful across the United States so that people could better understand their water quality impact or water quality issues and what does that mean for their health and also for their community as a whole. And then, so that's kind of where we ended it. And then we had a break, but come back from the breakout. But there was a lot of other points that were brought up as well, especially with trying to identify and address some of these issues. This includes discussions on some of the difficulties around doing some of these types of studies, everything from, similar to what Abner talked about with his talk, where you need a lot of different disciplines. And it's really important to have that interdisciplinary, cross-disciplinary approach and be able to address some of these very complex issues. To when you're looking at some of these potential exposures, there's also a difficulty with co-occurring contaminants that make your health studies even more complex. So how do you account for that if you're looking at it from an epidemiological perspective? And then in addition, some of our challenges are the historical records and being able to make sure that we have long-term records of some of our contaminants so that we understand what are the potential exposures. And that's where potentially having more communications across disciplines when we're trying to come up with sampling schemes to make sure that we're being able to best address appropriate environmental sampling so that it can address health-related questions and vice versa as well. And then in addition, making sure that we're also focused on some of those secondary compounds and those emerging issues that we're having, such as the PFAS and other things like that, where maybe they're not an issue right now, but 10 to 15, 20 years down the road, we start to realize what kind of an issue those things are. And so how do we potentially account for sampling to make sure that those types of things are taken into account as well? And then, always long-term studies. Mary has probably one of the best examples of, I think, of a long-term study in looking at potential health impacts. And so trying to do more modeling around some of those types of studies to make sure that we're actually being able to address some of those long-term health impacts and understanding what long-term exposure potentially looks like. And I think that's, and if I missed anything, if anybody wanted to jump in from our group, but I think that covers everything that I remember up to this point, but feel free to jump in if anybody had any additional thoughts or points that they wanted to make.
May I just some minutes, small comment. The work we do is really in villages, rural areas, and we found that it was the only solution to already have potable water instead of waiting for the government to take action. I am in Mexico. I don't know if the others don't know this because I told this in the group. So we don't have so many resources available because in every country, of course, nobody talked about the economics so far because we know we have all these contaminants, anthropogenic or natural. But of course, at the public level, there is a certain amount of funding available to solve this per home or per person. Maybe in the US, I throw a number and I would be very happy if somebody can provide more information. I think that in the US, you have available maybe, just thinking about this declarations from your new government, from Biden administration for tribal areas, for instance. I think you have a funding maybe in the range of $10,000 per family. I just throw the number, I think, from the top of my head. In Mexico, that is not available. I mean, maybe $500 maximum, or even 100. because this is a real limitation when you want to solve these problems. And my comment was, I just was going to tell this in the group, some of these contaminants are very easy to solve. Like the easiest of them all is nitrate. Like this is kind of not even, if they ask me, we're an association and we design filters. If you ask me, you can even have like a small jar with nitrate selective resin, less than $100. I mean, just throwing numbers like that. Huh? Once a month, you wash it with a little common salt, and that's it. I mean, nitrate is not a problem. It is much more difficult, the heavy metals. And for that, we use reverse osmosis. And if you have available pressure, like 30 PSI or 40 PSI, I think in the US, in the public supplies, you have a requirement of 60 PSI, the pressure in the network. With that pressure, you just use a simple RO without a pump. And I don't want to be too commercial here. We're a non-profit, but we know about these costs, of course. But it's like $200 for a home. So only drinking water. Eh? But I think in the US, there is a problem because the public authorities do not allow these point of view solutions. I mean, everything goes always to a central treatment system. But these are a couple of issues I wanted to mention. Huh? Like I wanted to give more details in our group, but now it's for everybody. So, but when I hear nitrates, it's not a problem. I mean, when I hear the word, it's so easy, just a small cartridge with not even half a liter of resin, that's it. I mean, it's really incredibly easy to solve, only for drinking water, not for all the supply. But I think in the US, you have a problem because there is the point of view is that all the water supply has to be potable water quality. So this was I would like people to really confirm or deny this or give some other ideas, but that could be a problem for the future. If you want all the water to be perfect quality, it will be very expensive and it will take years to get to that level of quality everywhere. Eh?
I think you bring up a really good point, which is the distribution of resources for addressing the problem are incredibly unequal across the globe. And especially in the context of climate change, where also the distribution of resources aren't equal. And so I think this is something that maybe on Wednesday we can revisit as one of the bigger problems that we've got to address is, you know, here in the US, the resources are going to be distributed differently and the regulations are going to be different as they are across the world. How do we deal with some of these inequities that are real? And I think that is something that Gabe brought up earlier today, as did others, is that we need to start looking at this as a broader global issue as well as not just a local issue for any of us. I'll move into our group. We had an interesting discussion. Some of it overlaps with what the other groups had to say. Jesse certainly brought up the interdisciplinarity issue and that we need that, as well as the education issue came up in both groups. And one of the things we talked about was a program that Nebraska's using right now with the issue of nitrates and how to bring in different stakeholders. And so one of the things we were talking about was you have all these different stakeholders. You have citizens that are also a stakeholder. You have the regulatory agencies in states where or countries where there's a lot of agriculture. You've got both the agronomists, the farmers, the farm workers are all part of that stakeholder chain. And that really what we need to maybe start moving towards is developing community-based participatory research that brings the stakeholders together along with the interdisciplinary scientists to build programs that occur at the local level, but there could be ways in which we use models such as the one that Crystal Powers described, in order to broaden out that effort. So, and I'm sorry, Crystal had to leave. So if I mess up her program, maybe somebody else from the University of Nebraska can jump in, or Jesse, maybe you can explain it as well. But it was a program that brought in stakeholders across all groups with the scientists, and then communicators to communicate what was going on, because as academics, we're not always the best at communicating the science, even for those of us that think maybe we are. And facilitators to facilitate the discussions, to see how the research moves forward and how the policy can move forward. And together, if we can bring those kinds of groups all into one room, we might be able to come up with faster solutions. So I think that was one of the really main points that I got, was getting everybody together in a room, but with appropriate communicators and strong facilitators to get the ideas out. The other issue that we didn't discuss, but I do want to bring up since I've got the stage at the moment, is this issue of the parsimony principle, and when is the weight of evidence enough to start moving these things forward, and how do we communicate that weight of evidence back to the stakeholders to circle back to the policy? Because I think policy won't change without those stakeholders being involved in pushing it. So that's it. But Gabe, was there more from our group that I'm missing?
I think you got the main parts. We did spend a little time about I think a point that I've never brought up and that kind of resonates with me is how to, so we talk about citizen science a lot, or civic science, and however you want to put it, but how do we make citizen science good enough to be adequate for protecting health, yet cheap and accessible enough to be used in reality with communities? I know Lex and I grapple with this all the time in our work on lead, but I'm sure many others have too. And, you know, when is good enough, and when is it just simply crap science that will leave people, vulnerable people, victimized actually by these burdens?
Right. And I think this is critically important. Lex.
Yeah, following up on Gabe's point, I think one obstacle is some members of the public health toxicology community, in the sense that when you create a standard, I know, there's a reason to have either a 10 or say a 50 ppb standard for arsenic in drinking water, depending on the country. But it's not that the health of, I think my colleagues in public health would agree that there's nothing magical happening when you go from 9 to 11 ppb or from 40 to 60. And yet, when I talk to an analytical chemist, maybe they are the real culprits. They tell me the kids are not going to distinguish 40 and 60. And I can't deny that, but I don't think that means the kids are useless. I've faced that a number of times in the past couple of decades.
Yes, and I think Alan and I have both faced that as well.
Yeah, I'd like to respond to the quality issue. That's one reason that we do split sample testing, and we share our results with the students, and they're able to do a direct comparison. And over time, that will build the quality of our citizen science teams. It's not something that's going to happen overnight, but it's an approach I think that could be used everywhere. Really, is to have a student do a test, have them send a sample to a lab, and then compare what they're getting to what the lab's getting.
You know, Dan, that's a really interesting point, and I'm glad that you brought it up. And that's really, really good. The interesting thing, though, I was just sitting here and I was struck with the. I think it's kind of it's an interesting catch-22, right? Because granted, we all recognize that the citizen science metrics are less robust. But I would agree, and I don't remember if it was Avner or Lex who just said it. I'm sorry, but I would totally agree that we're not talking about 51 versus 49. We're talking about 100 versus 0. We're talking about large sweeping variation. The other point that had come up relative to citizen science use is relative to what do you do if someone's deliberately obfuscating, or if someone's just completely not using the technology correctly, even if the technology is fairly simplistic. And it would seem to me that machine learning or artificial intelligence would be able, providing that you have a large enough data set, be able through either temporal or spatial or both variation, nearest neighbor type of approaches, be able to clean data sets substantially relative to that. So it's interesting because I think by getting back to the earlier point, and I'm going to just throw it out there, but it's many in the community, analytic chemists or toxicologists saying this isn't good enough are preventing innovation by which post collected data could be analyzed to make it more useful, which I think is interesting.
If I may jump into this and link some of the components that made, first of all, I think one of the revision I would see that I've seen so many times is the cost for, and it's related, the cost of water quality measurements. And specifically, I don't want to insult anyone here, but I'm going to say it, using commercial lab. But you know that commercial lab, when they measure, when you are a homeowner and you want to measure, and you really want to measure your water for the different metals, you pay by individual metal, even though it's running through the ICP and costs one run. So a cost that in my lab will cost me $20 will cost $1,000 in a commercial lab. This is unacceptable. And we need, one of the things to make it accessible to people is to make sure that this gap between the actual cost and the profit that goes into commercial lab is somehow mitigate, even by regulation or by state involvement, that make water quality measurement accessible even for poor population. I think this is one really critical that always strike me when I go and talk with even citizens or people who really care. Say, I cannot afford $1,500 now just to do once a year water quality measurement. And the state, if you go to the state, for example, it would be only major elements that they would do. And all those metals are not including in kind of the regulatory state service that they do for homeowners. So if they really care about the water, they go for a commercial lab and then they have to spend this amount of money. So this is one thing. The second thing I think it's important to emphasize is, it's mentioned earlier in one of the discussion, is the remediation technology and ability to treat the water. It mentioned that reverse osmosis would take care of metals, true, but it actually induces a really severe human health by using a reverse osmosis water without compensation of the magnesium salt in the water. There are many studies have shown that exposure to magnesium depleted water is associated with high death, sudden death, heart attack, and so on. And it's really extensive literature coming from Sweden and kind of Scandinavian countries, and the new studies from Israel showing that population exposed to reverse osmosis are having much higher heart attack in southern part of Israel. So it's very important when we are, I mean, I know it's kind of intriguing. We want to protect the people from lead or from other metals in the water, but at the same time, we have to make sure that the reverse osmosis device that we are recommend is indeed would benefit the health rather than to deteriorate of the people.
And just to add to that, I mentioned reverse osmosis once as a potential remediation process, and a lot of the water industry came down on me hard because it is energetically really expensive and has a large carbon footprint. And it just concentrates the toxins that you then or the toxicants that you then have to get rid of.
I would also add that reverse osmosis doesn't remove, at least not very efficiently, the most toxic form of arsenic.
Right.
So it's not really, I mean, I understand why we have to do treatment, but too often water consumers go straight to treatment as the solution. I think that's really a Band-Aid. I think we need to stop pollution at the source.
Right.
May I just say something? Just 2 minutes. Huh? The solutions that we have implemented in Mexico, we always are adding a cartridge with calcium carbonate and the magnesium oxide. So we really add calcium and magnesium, which is necessary. Eh? So this is an important observation that we have to put the calcium and magnesium at the end. We don't advise on drinking water with no salts whatsoever. Eh? So we really recommend, and we do it. And it's not a problem. Eh? It's just products that you buy, but the bag, it's NSF quality, all of these products. And concerning the carbon footprint, when you do it in the home, it's almost zero because you're using the pressure from the pipe network, from the water utility. So basically the water goes through the membrane, and the other quality, the reject water, when you do osmosis in the home, typically you will use a very high reject, a very low recovery, like let's say 15%, because you don't want to use any chemicals. So the membrane, you're not adding any chemical as an anti-scalant, and the reject water, you use it in the home, like for the bathrooms, etc. Yeah, like you can send it to the clothes washer, for instance. This is what we do in Mexico. Huh? So the water is not wasted. And as far as I know, it is the only way to use reverse osmosis without any of these environmental issues around it. Because I worry a lot if a town uses reverse osmosis for the whole town. You know that at least 50% of the water will be, you have to dispose of it in some way. And this is very difficult to do. But not when you do it in the home. It's kind of a natural cycle. You separate the water, pure water, concentrated water and then at the end of the day, all of this is thrown away in the waste stream. So basically you just, the humans and the pets, they had the good water and at the end of the day, you did nothing to the water, right? It goes back to the natural cycle. But these are some objections that I understand. At the municipal level, it's a bit difficult to manage, but not when you do it at the home level. But I'm sorry that to speak too much.
No, thank you. You know, and again, I think that point comes up that NGOs are very important in trying to come up with some of these solutions. And again, the issues are very different and the regulations are very different when you talk about different countries and even across different states and even across different municipalities. Virender, I saw you unmute. Did you have a comment? No, okay, Lex.
I have a question. I sort of alluded to it in a chat at the end of our general session, and I was wondering whether that might be discussing some more. You know, when I started working in Bangladesh, I have to confess, we collected samples and it took us a year to get the results back. There was about 6,000 wells and they were analyzed in the lab. We did it more recently and we could just test them in the field and give the result right away. I know of public health studies, epidemiological studies being conducted in Bangladesh today, funded by NIH, where households don't find out about it, more than they have to wait for a year for the result. And I think today that is inexcusable. What I'm wondering is how this could be avoided in the future. I mentioned in the other discussion group, PFAS, things that are difficult to measure, you understand. But something like arsenic, it's true for fluoride, people shouldn't have to wait. And maybe that's another way of introducing this notion of the usefulness of field kits. Maybe this is a question more for Mary. I'm curious to know what is the thought process within scientists at NIH working in developing countries in particular?
Yeah, well, most of my studies have been in the United States, but certainly I can just comment on what we've done, like in studies in the agricultural health study. If we did do a small amount of sampling of the wells, most of our estimates are based on model data, but if someone has a well that tested above, at or above the regulatory limit, we inform them as soon as possible. But you're right, sometimes there's a lag, samples go to the lab in batches, and it can be a matter of, months, hopefully not, certainly not as long as a year. That doesn't seem like that would need to take that long. So we, under our institutional review board, we say that we will inform the participants, and then we send a letter with the results. And we typically only do that when there's a health standard that we can comment on. Sometimes people request their information and we'll send that to them. And, but it's challenging when there's not a clear health message that you can say, because, there either isn't a regulatory limit or the science is still uncertain. But that's kind of what we do. And it's certainly important to get back to people. And in fact, that's an incentive for participation, is that you're going to get sometimes a very expensive well water test results for your home drinking water source.
I think, I'm glad you brought up IRBs, institutional review boards, because I wonder whether that maybe is something that should be pushed more, that an IRB actually has very specific requirements on how quickly things are reported. And I know for a fact in developing countries, it can take a year more if it ever comes back, unfortunately.
Yeah, that's a good point, because I think, I don't even remember if we had language specifically about a time frame, but it's sort of implied if you have a violation of a health standard, that you should get back to people as soon as possible. Yeah, so that's it's important to do that. And yeah, I think maybe IRBs need to pay more attention to that.
And possibly thinking outside of the box a bit, there are some programs out there that I think have made very large differences in people's lives in developing countries. And maybe looking at some of those programs that maybe don't necessarily have to do with this specific issue, but they are programs that have delivered rapid outcomes to large segments of the population. And the one I'm most familiar with is the Sustainable Rice Platform, but that's really worked well as a community engaged program to change the lives of nearly 1 million people now. And so looking at those kinds of platforms and how they manage to do that might be a framework we could use both within the US and more globally. All right, any other thoughts for today? I think we're hitting the end of our time. Actually, a little past the end of our time. We've had such a nice conversation. Nope, it's actually right on time. I think what we'll do is reconvene tomorrow morning at 9 a.m. and continue thinking. I think we've come up with a lot of really great ideas for moving forward. And I'd like us to continue thinking about it, and also continue thinking about how do we integrate the issues of climate change into some of our discussions. And with that, I really thank all our speakers today. Everybody just did a wonderful job in presenting the issues moving forward. And I hope everybody will be able to join us again tomorrow and Wednesday. Thank you, everybody.